Hello, and welcome to Teach Engineering. My name is Ariana, and I'm currently a sophomore at the University of Colorado Boulder, studying to become a biomedical engineer. Today, we are embarking on a journey to understand Newton's third law of motion. This law builds further on the first law that states, a body in motion remains in motion or a body in rest remains at rest unless acted upon by a force, as well as the second law, which states that a force equals mass times acceleration. Newton's third law of motion states that for every action there's an equal and opposite reaction. What exactly does that mean? Think about a box that's sitting on a table. The box is pushing down on the table due to gravity. In reaction to this, the table presses back up with what we call a normal force at an equal magnitude. These forces balance, so no acceleration of the box occurs. Today, our main objective is to identify something called an action-reaction pair. These are forces of equal magnitude in opposite directions that act on different objects. Free body diagrams are used to display the relative magnitude and direction of all forces that are being applied to an item in a certain scenario. Free body diagrams are also known as vector diagrams. In a free body diagram, the size of the error indicates the magnitude of the force, while the direction indicates the direction the force is acting. The exact type of force is labeled next to each arrow in the diagram. Typically, an item is represented by a box in a free body diagram, and the force arrow is drawn from the box center outward in the force directions. With this in mind, free body diagrams are very useful. How do engineers use free body diagrams? Engineers use them to draw and explain the simplified version of action-reaction pairs. These diagrams allow engineers to understand the basic forces acting on an object as they go through the design process. Let's put these concepts into practice. Think about baseball. When the bat hits the ball, what do you think is one of the action-reaction pairs that occurs within this action? The baseball forces the bat to the left, the bat forces the ball to the right. Together, these two forces exerted upon two different objects from the action-reaction force pair. Now, think about when you walk. There's also action-reaction pairs. Can you identify at least one? One of the action-reaction pairs is the fact that when you walk, a significant amount of force and pressure is exerted on the ground by our feet. The ground in response exerts an equal amount of force in the opposite direction. Let's conduct a demonstration using some basic things to illustrate Newton's third law in action-reaction pairs. All you need is a soda can, a nail, some string, and water. Use a nail to poke 4 holes around the base of an empty soda can. When the nail is in each hole, push the nail to the left or the right to angle the hole so the water will stream out on a tangent to produce thrust. Do the same for each hole, tie a string to the top. In the demonstration, fill the can with water and lift it with the string over a sink or a tub so you can observe the rotational movement of the can spinning as water flows out of the holes. Newton's laws are crucial since they relate to practical everything we encounter on our daily basis. These principles explain in detail how objects move and remain still. Everything around us moves according to Newton's laws, and because of this, we can explain things like how buildings don't collapse and how cars operate. Therefore, engineers apply Newton's third law to understand the action-reaction pairs when designing a wide range of creations, from rockets and aircraft to doorknobs and medicine delivery systems.
Check out the lesson video on Teach Engineering website, and then use what you learned about Newton's third law and action-reaction pairs in an associated hands-on activity, sliding textbooks.